All right, welcome everyone. Good morning, good evening, good afternoon. My name is Yuan Chao, and I am a researcher with Microsoft. So welcome to session number 2, physical layer design for batteryless and low power network sensor systems. So in this session, we will have 3 awesome papers talking about LoRa and backscatter communications and so forth. So the first paper is entitled AE-LoRa, towards ultra-low SNR LoRa communication with neural-enhanced demodulation. And the paper will be presented by Chenning Li. So Chenning Li is currently a graduate student at Michigan State University, working with Dr. Yunhao Liu and Dr. Zhichao Cao. So his research focuses on wireless networks and sensor technologies. So this is also the only one best paper award of this conference. So now let's welcome Chenning, and the baton is yours.
Thank you so much, Yuan Chao. Hello, everyone. My name is Chenning, and today I will present our work, the AE-LoRa, the neural-enhanced demodulation for LoRa communication. Recent years have witnessed the emergence of low-power wide-area networks, the LPWAN, as a promising mechanism to connect billions of IoT devices. And LoRa, Sigfox, and NB-LT are the 3 commercialized wireless technologies that facilitate the establishment of LP1s. Among them, LoRa, it achieves the long-range and low-power communication between the IoT sensors and the gateways. The key point is to modulate data using chirp spread spectrum, the CSS, in the physical layer of LoRa. From the sensor nodes to the gateway, CSS first defines a base-up chirp whose frequency increases linearly. Then it can encode data bits into the shifted initial frequency, as shown in the red lines. In this way, as a gateway side, it can adopt the D-chirp processing for decoding. First, it multiplies the chirp signals with the base down chirp, as shown in the green line. And then it applies the FFT on the D-chirp signal. Therefore, it can focus the chirp energy into the shifted frequency on the spectrum and decode the data bits by detecting the energy peak. In terms of the long-range and low-power communication, LoRa can supply the energy of noise by focusing the spectral energy on the spectrum, which allows sensor nodes to send data to gateways several or even tens of miles away. However, as the SNR gets lower and lower, we can find that the energy peak on the spectrum can be distorted or even overwhelmed by the noise energy, resulting in the decoding failure. From the sensor nodes to the LoRa gateway, we plot the chirp symbol decoding accuracy with different SNR conditions and the different configurations of LoRa, including the spreading factor, the SF, and the bandwidth, the BW. As we can see, the standard LoRa demodulation method, the D-chirp, determines a SNR threshold under which the chirp symbols cannot be decoded reliably. Generally, a larger SF enables a lower SNR threshold, which results in a longer communication range and larger energy consumption under the same bandwidth. Given the relationship between the SNR threshold and the communication range, the weak signal decoding has been a hot research topic in our field. For example, given the observed SNR of chirp signals and the threshold of the D-chirp processing, to avoid the D-chirp failure, most existing works aim to improve the SNR of the observed SNR of chirp signals over a weak LoRa link, as shown as the blue curve depicted in this figure. Such SNR gains are obtained by leveraging information collected from multiple LoRa nodes or gateways. Although these approaches have achieved impressive SNR gains, such gains are obtained costly if the LoRa nodes and gateways are not densely deployed. For instance, Quire leverages up to 36 co-located LoRa nodes to boost the received signal strength. Charm utilizes the spatial diversity of 2 to 8 gateways to decode wake chirp signals through the coherently decoding processing. Based on this observation, we can find that all existing solutions inspires us to think about this question. Can we optimize wake signal decoding by decreasing the SNR threshold directly? And how to achieve this? This motivates our work, AE-LoRa, a data-driven neural-enhanced demodulator. It aims to capture extra SNR gains by decreasing the SNR threshold of the D-chirp directly. Besides, it only relies on the single pair of LoRa transceiver and is orthogonal to all existing works. So in the following pages, I will introduce our work from observation, the system design, and the challenges. The idea of applying deep learning stems from our 3 observations. First, the chirp itself. As a neural-enhanced decoder, AE-LoRa takes as inputs the 2-dimensional spectrogram of chirp symbols, including the amplitude and phase information. Shown in this figure, we first collect 4 spreading factor 7 chirp symbols. They represent 4 different but very close data bits. To illustrate their signal difference more clearly, we plot the spectrogram on the differences of amplitude and phase. As you can see, although the encoded initial frequency among these 4 chirp symbols are close, we can clearly observe the unique energy peak distribution from the difference spectrogram. Additionally, we can see the peaks and valleys alternatively appear in both amplitude and phase information. Specifically, the patterns observed by amplitude and phase are correlated, and different chirp symbols exhibit diverse patterns. Hence, such a spectrogram pattern is a unique feature dimension to distinguish the different chirp symbols. We give the conclusion for this observation. It means that the spectrogram pattern makes it a unique feature for our neural-enhanced decoder. The second observation is about the robustness of our 2-dimensional spectrogram, including the phase and amplitude. As we know, in the standard D-chirp processing, it detects the 1-dimensional energy peak on the spectrogram. However, AE-LoRa takes as inputs the 2-dimensional spectrogram, which is noise resilient. Specifically, the energy peak distribution on the amplitude spectrogram exhibits a linear pattern, and even facing severe polluted noises, we can still observe parts of the energy peaks, which can be potentially learned and recognized by our neural-enhanced decoder. So that means AE-LoRa can still recognize it even with partial energy peaks. So this guarantees the robustness of AE-LoRa. The third observation is a finite feature space of LoRa chirp symbols. Since we know that LoRa can only encode a fixed size of data bits under certain configurations. For example, for spreading factor 7, it can only encode like 2 to the power of 7 equals to 128 different codes. Thus, such a finite feature space can fully exploit the learning ability of deep neural network, the DNN. Moreover, the finite feature space is robust across different environments. For example, given chirp symbols from different periods, different nodes, and different environments, our trained DNN can always recognize the encoded chirp spectrogram due to its fixed pattern corresponding to its encoded data, as shown in this figure. So Based on, this is the third observation. We have the finite coding space of LoRa for data-driven AE-LoRa. Based on our three observations, we designed the system framework of AE-LoRa by incorporating the chirp knowledge and deep learning. For the first step, upon receiving the raw signals from the sensor nodes, AE-LoRa first adopts signal processing for chirp symbol generation, including the packet identification and offset recovery. Then it feeds the offset-free chirp symbols into our neural enhanced demodulation, covering the spectrogram generation and DNN-based demodulation. Finally, it outputs the decoded data bits for each LoRa packet. Before we do the chirp symbol demodulation, the first challenge is how to get the chirp signal, how to get the chirp symbols, how to detect the packet accurately. Given the preamble of the LoRa packet, say 8 base-up chirps in a row, we propose to accumulate the energy of all 8 base-up chirps on the spectrum, thus it can detect the packet under extremely low SNR conditions, which cannot become the bottleneck of our following DNN demodulation. However, accumulating the 8 base-up chirps is non-trivial due to the random initial phase of each base-up chirp, resulting in the destructive accumulation on the spectrum. To achieve the constructive accumulation of those base-up chirps, we design a phase searching algorithm for accurately compensating the phase offset over multiple base-up chirps. It can not only detect the preambles reliably, but also compute the offset of the whole packet accurately. After this, we can divide the whole packet into a series of offset-free symbols. The second challenge is to deal with the severe noise and low SNR conditions. Since you cannot expect the DNN to recognize the spectrogram pattern directly. At the beginning, we tried the signal processing-based filter for noise reduction. It aims to extract the primary components of the chirp symbols. However, as you can see in this figure, it can only remove noise and a relatively higher SNR, around -10 to -15 dB. In contrast, we design a mask-based DNN filter, which is a data-driven filter and can derive the clean chirp symbol even under low SNR, such as -20 dB. The last challenge is the whole DNN design of our neural enhanced demodulation. Given the raw spectrogram with amplitude and phase information, we show our deep neural network design with intermediate results. As mentioned before, the first part is a mask-based DNN filter. As we can see, we just designed different CNNs, LSTM, and dense layer for our mask-based DNN filter. As you can see, although the input spectrogram is noisy and cannot be distinguished by human eyes, our DNN network can gradually recognize the linearly increasing pattern for chirp spectrogram. It outputs a mask, and we need to multiply it with the raw spectrogram to reduce the noise. Upon receiving the clean chirp spectrogram, we design another spectrogram-based DNN decoder, which can exploit the finite coding space of LoRa symbols and outputs the correct decoded data bits, as shown in this figure. So we start our implementation and evaluation from this page, including the indoor platform in a building and the outdoor experiments at a campus. We adopt the commercial LoRa sensor nodes, and in terms of the evaluation metrics, we care about the symbol error rate of LoRa and different SNR conditions. The SNR gains for SNR threshold when the SER equals to 10%, and the corresponding battery life of gains. All these gains are computed based on our baseline, the standard D-chip processing. So the first question about our evaluation is that how much AE-LoRa improved the demodulation performance than the D-chip processing and the various LoRa configurations. we first showed SER and corresponding SNR gains in this page. As you can see, AE-LoRa outperforms the baseline for all testing configurations. For different SF, the spreading factor, the SNR gains is ranging from 1.84 dB to 2.35 dB. Besides, the SNR threshold of AE-LoRa at a spreading factor can almost catch up with the D-chip processing at a higher spreading factor. For example, the SNR threshold of AE-LoRa at spreading factor 7 is close to the D-chip's performance at spreading factor 8. We further evaluate the battery life for AE-LoRa and the baseline. We can see that all the green lines for AE-LoRa are higher than the red ones, resulting in a consistent battery life gains for different SNR conditions and LoRa configurations. Next, we answer these two questions. How effective HK technique incorporated in the design of AE-LoRa? Shown in this figure, AE-LoRa suffers by removing the mask-based filter or spectrogram-based decoder. An interesting thing is that we cannot incorporate DN filter with the D-chip processing, which underperforms in comparison with our DN decoder. Further, we evaluate the robustness of AE-LoRa, in which we apply our trained DN model on new data from different periods directly, without model retraining. This SER-SNR figure shows that AE-LoRa outperforms the baseline consistently due to the finite feature space of LoRa chip symbols. The last question is about outdoor performance of AE-LoRa. We first collect the LoRa packets from 6 positions at the campus and run our end-to-end system from the packet detection to the decoded data bits. As we can see, compared with the baseline, the original AE-LoRa decreases SER of the D-chip for all 6 positions. Besides, we also retrained our DN model, which achieves a little better performance than the original one by capturing more unseen noise patterns. This demonstrates that we can further improve AE-LoRa by updating it in an online or distributed manner as more packets are collected across multiple gateways. So to conclude our paper, we present the design, implementation, and evaluation of AE-LoRa, a neural enhanced LoRa demodulation system that breaks the SNR threshold of the standard D-chip processing. The SNR gains enable longer communication distance and battery life in LoRa. Thank you.
Thanks, Jenny, for the great talk. So, any questions from the on-site audience? I cannot see if you raise your hand. Please just ask a question directly. I see someone is walking to the front.
Thank you for the presentation. So I have a high-level question. If you keep pushing this, will we break the Shannon theorem?
You mean just to achieve a lower SNR threshold for LoRa decoding?
We know that there's Shannon capacity theorem relates, right? Do you think that we can go beyond that?
No, of course not. Actually, we just compute the limits for the SNR thresholds. Actually, if you just apply the D-chip processing on a very clear environment, it should achieve the limits for the LoRa demodulation. The thing is that we have the noise. I mean, we have the impact of noise on the environment, which can just induce the performance for the standard D-chip processing. We also observed that the thing is that due to the data-driven decoder of deep learning, it can achieve a better performance to avoid the impact of noise on the D-chip processing.
Okay, thank you. Another question, I understand you have tested it in a different environment, and I suppose your training also consider different sources of interference and noise. But can you know for sure that there will not be an adversarial scenario that this just failed miserably?
Actually, at least from our testing beds, I mean the indoor test bed and the outdoor test bed, we can say that at least from the indoor test bed, it performs well. I mean, consistently, just delivers a lower threshold. However, for the outdoor environments, we still can observe that we need to update our neural enhanced decoder online or just to achieve a better performance. It seems that we still cannot capture all the noise patterns in the environment. Okay,
so is there something like ongoing work to look into that, or?
Yes, definitely. Actually, we're trying to incorporate AE-LoRa to achieve it in a distributed method. For example, just incorporate the federated learning with AE-LoRa. In this way, we can just collect data from multiple gateways. It's kind of like the coherently decoding processing with existing works. That means we can just incorporate AE-LoRa with all of the existing works into a whole system.
Okay, thank you.
Yeah, before someone asks the following questions, I want to let everyone know, including the online audience and the local audience, that you can go to our Slack channel and leave your questions there. Yeah, we got someone actually ask questions on Slack channels. 2 quick questions. So this is from Hua Tao Xu. So how many samples are required for model training? How about the computational overhead in the resource constrained devices?
Yes, good question. Thank you. For the first one, actually, we just train our model using like 40,000 symbols, but it's for spreading factor 7. And if you just want to train it with a higher spreading factor, it requires more symbols, at least, I mean, maybe just around 5 to 10 symbols for each kind of encoded data bit. And for the second question, we test our model, I mean, our trained model on the PC and the Raspberry Pi. And we cannot say that it achieves the real-time decoding for our neural enhanced decoder. But the thing is that we expect to compress the model in a more efficient way. And we already try some simple strategy to compress the model, and it achieves it just saves the time consumption for the testing processing. But I mean, in my opinion, I think we can still just optimize it and try to achieve a real-time processing for the testing processing.
That makes sense. Yeah, just want to double click on that for the decoding part of it, right? So do you really need like a GPU to do the decoding at the gateway side?
Oh no, you don't need to. Actually, you just need to put the trained model into the gateway, for example, like a Raspberry Pi or something like that, and try to the decoding processing. You don't need to retrain the model. So that's why we care so much about the robustness of our model, because we just want to apply our model directly without the data recollection or just the model retraining.
Got it. Okay. And another question that I have is that we know that DN is gaining popularity, right, in wireless communications, and quite a few people are trying to use DN for decoding or scheduling and congestion control, a lot of different kind of scenarios. So do you have any insights or experience that you want to share with us on how to design an effective and efficient DN models in the context of wireless communications, right? For example, if I recall correctly, you replace SDM with GRU in your DN model, and maybe you can share the rationale behind that, or anything that that you find in your experiments that would be helpful to the others?
Oh yeah, of course. Interesting thing I get from my experience is that for the wireless signals, I don't think that it's possible to put the deep learning techniques into wireless communication or sensing directly. The thing is that we know that the wireless signals just experience the severe noise in the background, I mean, in the environment. So that can explain that why we have two parts for our neural enhanced decoder, the filter and the mask-based filter and the spectrogram-based decoder, because at the beginning, when we just try to feed our DNA decoder with raw spectrogram directly, it performs so bad. And I realized that we have to give some clean spectrogram into our decoder. In this way, we can just fully exploit the learning ability of deep learning, because it can just, it's kind of like you input some clean images to the DNA decoder, and then it can just output the satisfying results. So that can be, my opinion about the incorporation between deep learning and wireless communication is that you have to incorporate some wireless knowledges, for example, the noise reduction or the primary component extraction, to do some pre-processing for the following DNA tasks.
Right. So essentially, a certain kind of pre-processing is definitely needed before feeding the wireless communication signals to a DNA model, right?
Yes,
so we need to use domain knowledges to do this kind of, to do the right pre-processing so that we can make the DNA-based processing actually sensible or accurate.
Yep.
Okay. I guess we don't have any other questions. I want to thank Chenning again for your great talk and for the great work.
Hello.
Oh, go ahead.
Hi there. I have a question. Thank you for the presentation. I was curious about. I don't know. I'm missing something, but because I was curious about what is the performance of your implementation on the higher spreading factor. With, for example, if you have using spreading factor 10, so you will have 1024 chips in the LoRa chip. So is the performance in SF, higher SF will be better than lower SF or not?
Yeah, that's a good question. Actually, I don't think that the performance is related to the spreading factor. It's about the noise patterns. I mean, the size of your training data size, and we expect that our neural enhanced decoder can achieve consistent performance. I mean, for different spreading factors. I mean, I don't think there is. I mean, you can achieve a better performance with a larger spreading factor. It's all about like the noise pattern in your training data set. And actually, we didn't test our model for spreading factor like 11 or 12. The thing is that we have to change the output size for our neural enhanced decoder, and it can increase the cost for training processing, and it requires a large amount of data for our training processing. So it can also be regarded as future work for our paper, but we expect, I mean, in conclusion, we expect that our neural enhanced decoder can achieve a consistent performance based on different spreading factors.
Thank you.
Yep.
Any other questions from the local audience? All right, so let's thank Jenny again, and great job. Now let's move on to our second paper. So the paper will be presented by Ali Safari from University of Washington. The paper is entitled Multistatic Backscatter Networking for Battery-Free Sensors. And Ali is currently a fourth-year PhD student in the ECE department of the University of Washington. And he received his undergrad and master degree in electrical engineering from Sharif University of Technology in Iran and the University of Washington in 2017 and 2021, respectively. So his PhD research is focused on the design and implementation of battery-free sensors from human occupancy detection in smart home applications. So Ali, please get started.
Thank you for the introduction. Can you see my screen?
Yes, we can see the first page.
Hello, everyone. My name is Ali Safari, and I'm a PhD student at the University of Washington. Today, I will be presenting our work wherein we design and implement a multi-static backscatter network for battery-free sensors. Our proposed system can cover a wide area and the throughput is high. In addition, we design a modular battery-free sensing platform, which is compatible with our multi-static network. This sensor can accommodate many modalities like image sensor, microphone, and we have provided our files at this link. Before explaining our design, I would like to describe our vision. Many wireless battery-free sensors are deployed in an apartment. These green circles. These sensors can be low power, like temperature sensors, or power-hungry sensors, like image sensors. And the data size for the image sensor is high. So this imposes a limit on selecting the communication protocol. We have to choose a low power communication to enable battery-free sensing. Also, we cannot lower our throughput to improve the range because in some applications, the data rate is high, like image sensors. And the proposed system shouldn't be very expensive because we want to deploy many of them in the area. And the system should be scalable. In other words, if we want to expand the network, it should be easy to expand. To design such a network, we can use active radios. This figure shows 13 sensors nodes with an access point here. These sensor nodes communicate with access point via Wi-Fi, BLE, or LoRa, or any other protocol. Access points here is not expensive, and the communication range is high, especially Wi-Fi and LoRa. The system is scalable, and you can expand the coverage, and it can support high data rate sensors. And in the network, we have only two devices, an access point and a sensor. So the deployment should be easy. You just need to deploy the sensor where they can communicate with the bases, with the access point. But the main problem here is that the power consumption here is high for communication because the sensors need to generate a high frequency signal, like at 900 megahertz or 2.4 gigahertz. So it's not good for battery-free sensing designs. Before introducing the second approach, we need to learn about backscatter communication. This figure shows a backscatter system where a transmitter generates a high frequency carrier, a sensor node reflects that carrier and the receiver demodulates the signal and decode the data. Here, the sensor node does not need to generate any RF signal, so the power consumption is low. In the second approach, we use backscatter communication. This figure shows the floor plan, one RX unit and one TX unit. We address the power consumption problem by using backscatter system. However, this method has multiple issues. The coverage is short because the signal travels 2 times from the TX unit to the sensor node and from the sensor node to the RX unit. Also, the TX unit generates interference at the RX unit, which can be overwhelming for the data signal. There is a trade-off between range and throughput. In LoRa, backscatter range is long, but the data is low. So we have in this network, we have 3 devices, TX, RX, and sensor node. So the deployment is a little bit hard. So far, we have seen that active radio is not a good option because of power consumption, and backscatter systems have multiple issues. In this work, we propose Multistatic, a network of low-cost RX and TX units to communicate with many battery-free sensors over a wide area via backscatter technology. This figure shows our setup. We have 2 RX units, 6 TX units, and 13 sensor nodes. As you can see here, we have 4 types of signal. First, the back channel signal, which is the command from RX unit to the TX unit. Then the TX unit generates a carrier signal. And finally, the sensor uses its RF switch to modulate the signal, backscatter signal. And we have backhaul, which is the communication between the RX unit to manage the network. So here, the power consumption is low. Our coverage area increases as we add more base units. And as I mentioned, that the deployment for backscatter systems is a little bit hard. We designed a simulation tool that can generate a coverage map. So it helps me deploy the system. So how does our system work? Here is a communication cycle of the system, a single TX, a single RX network. Here, the RX, TX, and the sensor. First, the RX unit selects the optimum values for the frequency here and for the power to minimize the packet error rate. Then the RX unit transmit that activation packet to the TX unit. In the activation packet, we have selected frequency and power, tag ID, tag command, and communication duration. When the TX unit receives the packet, it wakes up the sensor node by transmitting the command to the sensor. And finally, when the sensor is up, it backscatters data to the RX unit. So now we want to add more TX units to expand our coverage area. Here, we added a TX here to support this sensor. In this network, here we have 4 TX units, 2 sensors, and 1 RX. The left table, in this system, the RX unit needs to select the best TX unit for communicating with a sensor node. For example, here for sensor 1, if we use TX1, the success rate is 0.95. So in the communication cycles, we choose TX1 to generate the RF signal for this sensor. For sensor 2, TX3 and TX4 have a high confidence score. So we can use both for communication. Finally, we want to add more RX units to expand the coverage, because adding more TX units and improving the coverage has a limit. For example, in this floor plan, we added an RX unit and TX unit here to communicate with this sensor. If we, this communication would not be possible if we didn't add the RX unit. So RX unit is necessary here. And if you want to cover a large area, we break down the area into multiple sections and assign one RX unit with one or multiple TX units to each section. For example, here we have RX1 that has 4 TX units and 2 sensor nodes, and RX2 that has 2 TX units and 1 sensor. This is the backhaul signal that manage the network. We learned how the communication process happens, but as mentioned, deployment is a big problem in backscatter systems. To address this challenge, we developed a simulation tool that can generate a coverage map based on the inputs. Inputs are the geometry of the house, the setup, and the position of RX and TX units. For example, here on the left, we have 3 TX units and 1 RX unit. The color is bright, which means the communication success rate is very high. White is 1 and dark is 0. Here we have only 2 TX units, so we anticipate that the coverage should be worse than the left setup. So here you see darker colors here. So it helps us how to choose the position. Let's see how the battery-free sensors work. We want to design a battery-free sensors that can accommodate many modalities and communicate with the sensor, with the base units. Here is the block diagram of battery-free sensors. We have the downlink radio that receives commands from the TX unit, the tag ID, the command that we had, that we have seen before. And we have a harvester unit that harvests energy from ambient light. And we have external sensors for extra sensors. Like if you want to add a sensor to your platform, you can use those extra pins to enable this. And we have the backscatter part that can communicate with the base station with the data rate of 250K. Now we used MCU here instead of FPGAs because in sleep mode, MCUs are better than FPGAs. And also we have some gating protocols to make sure that the power is good. For example, we add a motion sensor to a camera and we only turn on the camera when there is movement in the setup. Here are our boards. We have the TX unit. We have the RX unit that has a Raspberry Pi 4 process, and this is the radio. We have the basic sensor node, and these are the external pins that I mentioned. We have the harvester here, a microphone here that are mounted on the sensor node, and we have harvester here and image sensor here. Now we want to measure the power consumption of the camera. This plot shows the power, the energy that the camera needs for capturing and sending an image. X-axis is time in second, and y-axis is power in milliwatts. This big part is for taking a picture. So the sensor takes a picture, goes to deep sleep mode, see the power consumption is low, and when it receives command from the base station to transmit the image, it starts transmitting the image. This is one part of the image. We have 12 different sections. One part is a big part of the image. And here are two samples with our battery-free image sensor. Also, we measure the power consumption for microphone and environmental sensors. We have the idle power, deep sleep mode, which should be very low, sensing energy, communication energy, and also we use two different solar panels to power our sensors. For example, if we use a small solar panel, every 280 seconds, we can transmit one image. But if we use the bigger one, every 17 seconds, we can send an image. The environmental sensor is very low power. So if you use the small solar panel, you can transmit data every 1 second. To measure the range, we set up the system in a hallway and place the sensor node in the middle of it. This is the floor plan. We have the sensor here, RX and TX unit. We place the RX and TX units at the same distance from the base station, from the sensor node, and transmit 1,000 packets using 4 different data rates. As you can see, when the data rate is 250K, the coverage, the distance is 100 feet. And if we use a lower data rate, the range can be 150. To show that our system can cover a wide area, we set up the system in a 2-floor educational complex with area of 23,000 square feet. We have 20 TX units, the blue squares. We have 5 RX units and 130 test points, green points. At each point, the packet rate is less than 15%, and this system costs only $569. I would like to finish my presentation by reviewing our contributions. We presented the first multi-static backscatter system for battery-free sensing. We developed a coverage simulation tool to help us with deployment. And we covered a big area with a setup that only costs $569. Thank you.
Thank you, Ali, for the presentation. Yeah, any questions from the local audience? And for the remote audience, please feel free to send your questions in our Teams channel.
So, hi, this is Andreas Biri from ETH Zurich. I have 2 brief questions. The first one is there an inherent reason why you seem to leverage more TX stations than RX stations? Because it seems that if you have multiple TX stations, they might also interfere. And because you just want to increase yes and R basically, what is the advantage compared to using fewer TX stations and a lot of RX stations?
One reason is that the RX units are more expensive because they have Raspberry Pis, and also for the interference. So one TX at a time generates the carrier in a section. So they don't transmit data at the same time. So the interference is not a problem.
All right, thanks. And the second question would be, could you tell us something about the deployment challenge you're facing when you have to deploy quite a sizable amount of infrastructure in these places? Like, is it easy to find appropriate places, or did you find this hard?
The big problem in Backscatter is the TX interference. So in our deployment, we try to set up the TX unit in a way that they don't have direct line of sight. So they cannot see each other. So the TX carrier signal is not very strong at the RX unit.
All right, thanks.
Right. Let me ask another two questions. The first one is, are there any coordinations between different transmitters to minimize the interference on the sensor node, or it's completely? There's no coordination between transmitters. Because although you divided the area into different spaces and say, hey, this sensor node will be covered by this transmitter, if they are transmitting at the same time, they will cause some difference, interference at the receiver side, right? So are there any coordination between transmitters to decide when should I transmit, when should you back off, or any coordinations in your design?
Yeah, good question. The RX units control do this task. They choose the best TX unit and let them transmit the carrier signal for a specific duration. So when the RX unit sends the activation packet to the TX unit, it says, for example, for 100 milliseconds, generate the carrier and then go to sleep.
Okay, so there won't be more than one transmitter transmitting signals at the same time.
Yes.
Okay. And another question that I have is, I'm curious to see if your system is able to handle mobile nodes, or what if the environment is changing or there are furniture moving around in the space. How frequently do you, for example, need to update or reprofile the wireless propagation status, or update this coverage map? Or maybe you're assuming that the sensor nodes are always static and there's no movement in the environment.
Actually, we have handover. Let me share my screen real quick. So the handover is when a sensor node moves to another section. So we have a server that controls these movements. For example, if RX unit 1 cannot communicate with sensor 1 anymore, the server asks RX unit 2 to try to communicate with the missing sensor. And then we can find the sensor location in the network.
I see. So essentially, if one transmitter lost the connection with one particular sensor or receiver, then it asks the other transmitter to try to see if you can communicate with that particular node.
That's correct.
And once the communication is established, then this node becomes essentially in the coverage of the other transmitter.
Yes.
Okay, okay, got it. Thanks. And any other questions?
Yeah, I have a quick question. What is your multi-asset strategies if you try to communicate multiple tags at the same time using multistatic backscattering?
One thing that we can do is using different carrier frequencies for each sensor. So multiplexing in frequency. But it's a little bit complicated with this Raspberry Pi doing and the radio that we have to have a wide filter.
Okay, so does this answer your question?
Yes. Thank you. Thank you, Ali.
Okay. Yeah, thank you, Ali, again for your great talk and work. Now let's move on to the last paper in this session. So the paper is entitled Cocoon, a conductive substrate-based couple oscillator network for wireless communication. And it will be presented by Xingda Chen. So Xingda Chen is currently a PhD student in the University of Massachusetts Amherst, working with Deepak Ganesan. So his research focus and interest is low power wireless network, where he had research and industrial experience in building novel wireless architectures for ubiquitous sensing and app communication. So prior to UMass Amherst, he was with Boston University, where he received his bachelor and master's degree in electrical engineering. So Xingda, the baton is yours.
Thank you very much, Dr. Xu. And good afternoon, fellas. Today, I'm going to tell you how to only spend $50 in the world to precisely synchronize a wireless network. My name is Xingda Chen, and here's our project to build a couple network using conductive substrates. We look at how Internet of Things and wireless sensor networks are designed. Traditionally, these devices work as discrete elements. We assume parts like low power processors or energy harvested sensors would communicate and coordinate by radios, no matter how large scale the deployment is, or how small and low cost these devices are got to be. But in this paper, we look at the network slightly different and have a less traditional view of what a central node might look like. So there has been some significant developments in conductive substrates for the last decades. And we have used these kind of substrates to interconnect sensor nodes over a large spatial footprint. For example, we have conductive fiber interconnect wearable sensors, or we have paint or ink for some novel connections. What these materials provide is a new way to look at network center. Rather than being a collection of small individual elements, we see this network as the sensor being interconnected across these kind of conductive materials. So for example, we can have this smart clothing with a number of sensing elements interconnect by the conductive threads. We can have these smart home sensors interconnected via a conductive wallpaper, or a smart textile mesh for agricultural monitoring. And the advantage of using the substrate is the ability to synchronize these nodes. On the surface of the substrates, when I have a bunch of these devices that are interconnected across the space, I am able to work them in a synchronous manner. And this can give us some sophisticated operations like beamforming or synchronous sampling. For example, we have the idea of asset management in a warehouse. Traditionally, we will need things like an Ethernet cable to synchronize multiple RFID reader network. Now we have the conductive substrates. We can do the synchronization in a much cheaper manner. Other synchronization operations like distributed audio sampling or beamforming might be also possible, and we may be able to do them cheaper by leveraging these larger surfaces. Now you may ask, why don't we do the synchronization over the air? After all, we know how to synchronize a set of distributed nodes. Well, two basic ways for distributed synchronization involves with either using the data packets and process the received known information to adjust each device's clock, or attaching some additional analog hardware to track, process, or amplify the broadcasted RF wave and directly use it as the synchronous source. But when we look closely, and these approaches come with complexities. For example, demonstrated here using preambles as one of the packet-based synchronization methods to align distributed clock signals. In general, there's a trade-off between the synchronization accuracy and the length of synchronization preamble. The length of the data packet is already scarce in many IoT communication scenarios. Oftentimes, our data spectrum is very precious. On the right is an example of another approach to receive the envelope of a broadcasted clock. And this requires more hardware costs, and there may be signal processing requirements, as well as energy consumption, in which these complexities make it difficult to have these approaches become scalable. For novel unconventional wireless communication network, we need to have more flexibility to bring in tangential applications that adapt to complex environments and use cases at a scale. So our goal here is to synchronize RF transmitters and receivers that are spread out spatially across a large surface. And we use a surface, its large area, as a means to physically interconnect these devices. But we don't want to have our substrates work as a wire, as it would then introduce another wire network interface. We want to create interconnections for synchronizations without using any sort of network stacks. So what we are looking for is something that has zero overhead, simple, and almost like analog stipulation approach, where we have a sort of carrier on the surface and have all my nodes frequencies pulled to that single carrier for synchronization. So this is the basic premise to our design. We want to synchronize a number of oscillators in frequency to create a single shared virtual oscillator over a conductive substrate. While this technique we use for synchronizations is an old idea, biological systems like firefly synchronization with each other by coupling, and this is also used in integrated electronics design in the methods called injection locking. But we look at new ways for this approach to do frequency synchronization across a bunch of other elements throughout the surface, to see how exactly can we make these many oscillators pull and share into one frequency. We look closely at what on the substrate with two oscillators are going on. By sharing oscillators across the same node on the surface, we will have coupling through injection locking. In our case, we pull the frequencies of all the oscillators on the substrate via injection locking and have all the nodes work under the same synchronized resultant frequency. This phenomenon can happen is because the characters of reactive elements in an oscillator that will self-adjust its phase inconsistency when a Fourier resonation is injected to the tank. However, there are a couple of challenges we need to tackle to have the injection locking work in our favor to create a sophisticated RF network. Specifically, we have two challenges we need to solve. The first is that we need to figure out a way to precisely control the coupled oscillation. You know, an RF wireless network usually required precise frequency to operate correctly. And simple injection locking may converge to one frequency, but it's difficult to predict or control what precisely the resultant frequency is. How we pull and where the frequency settles depends on the power and bendability of the oscillator, as well as what frequency we started with. Problem is, the frequency difference between participating oscillators can be ambiguous. A 1 megahertz oscillator can have ambiguous frequency error up to 45 kilohertz above or below. This means an ambiguous free-running oscillator makes an ambiguous pole frequency that we cannot use. Additionally, the resistance between nodes, power dissipation, and all factors that will affect how much energy gets injected into a specific oscillator also determines where the frequency settles. This is difficult to model and compute for an accurate results, and this leads to ambiguous pole frequency. And our approach to this problem is to control the pole frequency by pairing many low Q slave oscillators with a high Q master oscillator. Low Q slaves has much larger frequency polling range than the high Q oscillators. With this, the more power we inject to the low Q ones, the larger it can be pulled to another frequency. If we use a single, very high Q master of high power, then all our slave low Q nodes will converge to the known frequency. From the cost perspective, cheaper oscillators that we want to use in the system has lower Q index. A precise oven-controlled crystal oscillator would ensure a high accurate output frequency for a node. But these oscillators shown in the curve cost hundreds of dollars a piece. A ceramic resonator costs 50 cents, but the frequency drift is too large to be useful for an oscillation. So by pairing many low Q slaves with a single high Q oscillator on the substrates, we can deal with the large swing while it still ensures a highly accurate, precise synchronized frequency. The second challenge we need to solve is we need to ensure that our frequency polling system is operating at an optimal power budget, which is particularly important in low power sensor networks. So when the high Q pulls a low Q, the amount of injected power from the master affects the synchronization states. In the case of two oscillators, one high Q master and one Q slave, how much power does my master output affects the result frequency waveform? I give a lot of power, the frequency is going to be very clean. Now, if I give little power, then it makes many sidebands between the frequency of the low Q and high Q. In time domain, I will have frequency ambiguity and varying instantaneous phase degree. They will be beat frequencies and it won't be good enough for synchronization. So what we need is a way to monitor how well it's synchronized and adaptively adjust the power to avoid scenarios like shown in the bottom right at a small energy expense. We have the master monitors the synchronization states by looking at the spectrum of the wave across the substrates demonstrated here. With small amount of power, there are spurious sidebands across, even made the high Q oscillation frequency is not the dominant wave. As I increase the injection power from the high Q oscillator, sideband starts to decrease and finally disappears if I put in large enough of power into it. So we introduce a measure called quasi-log distance to quantify the state of our synchronization. Quasi-log is a state where there's little instant phase variation and the variation changes very slowly across. The resultant pole frequency is almost as good as a pure tone and useful for wireless application. In frequency domain, the dominant frequency in its sidebands in quasi-log states decreases linearly. We define the quasi-log distance to be the largest distance between the peak of any sidebands to the line connecting the master frequency and the peak of the further sideband. So the more synchronization the system is, the lower the QL distance. We then monitor and empirically determine the threshold to decide the quasi-log states. Using this method, we can stop inputting power once the master learns that it reaches the quasi-log states. Here are some snippets of our implementation. We build 13.5 megahertz oscillators and we validate our design onto multiple substrates. We also validate the usefulness of our technique by using it onto a synchronous RF design. Here is a comparison between the power required to achieve quasi-log versus fully log. For 3 oscillators we tested that require power on 3 different substrates. And there is significant amount of power saving if we get our system to quasi-log than to fully log. Here we put Cocoon into application. We use the cheapest oscillator we can find on the market and see if Cocoon can improve the communication performance with frequency pooling. We supply each of our RF phase log loop with reference frequency that is synchronized through frequency pooling across the substrates. And the output signal are modulated with synchronous RF carrier. Here's a more detailed demonstration of how we can steer our RF frequency to micro-adjust its carrier frequency offset for synchronization. For a phase-up loop, a small perturbation in reference inputs will steer the outputs of phase frequency detector without the feedback system go unstable, shown in the figure on the right. An increase of 70 kilohertz in reference will increase the RF outputs 1.5 megahertz. We use this relationship to adjust our RF carrier and cancel the carrier frequency offset. We synchronize our reference input across the substrates and feed these synchronous 13.5 megahertz frequency to the phase-up loops on the surface. We use Cocoon to build a multistatic backscatter system. Here we have distributed emitters and receiver, and synchronization is important between the emitters and receivers because we need RF synchronization to cancel carrier interference and have the receiver down converts accurately. We tried 20 combinations of different ceramic resonators and record the distribution of our RF phase mismatch and the bit error rates of our backscatter communication. The result is very good. 90% of our phase mismatch is under 0.1 radians and 90% of our bit error rates under 0.001, which is a significant performance improvements when compared with the exact same setup but without frequency pooling. We compute the results with sharing single source clock through wallpaper and commercial solutions such as octoclock from National Instruments. Cocoon performance is comparable as if one drives all nodes with single source, but our implementation cost is much cheaper. We also compare our technique across other solutions. Although our phase error is slightly higher than works from VU and MegaMIMO, the equivalent signal degradation is still in the very acceptable range, but we had to achieve it with a significantly lower cost. So in conclusion, here is how we build a synchronization network using injection pooling on the surface. And we get to do that and achieve very good accuracy while keeping the cost at around $50. And thank you all for the kind attention to my presentation.
Thanks, Xingda. Very nice work. So any questions from the local audience? Yeah, probably I can get started. So it seems that this QR distance, right, is a key to ensure to the design, which ensures the quasi-log. Can you maybe elaborate a little bit more on how you set up the threshold for the for QL distance and adaptive power control algorithm?
Absolutely. So the definition for quasi-log isn't binary. So it is not, the system is not synchronized or not synchronized. Rather, it is a sort of a process from highly unsynchronized with a very fast beat frequencies to exactly synchronized with no beat frequency at all. And quasi-log is a state where the resultant waveform is super close to a exactly same exactly perfectly synchronized. So what it defines, here in quasi-log is a linearly decrease in frequency domain, and we sort of observe that our resultant frequencies, it's changing slowly, and then it is not affecting our RF performance. So what we do to determine synchronizations using our quasi-log distance is we empirically determines the distance by running preliminary experiments, and determines that the quasi-log distance of a number of 6 would affect to become quite a stable oscillations for reference to provide a reasonably really well RF performance, and works almost as much as like a single source synchronization.
Got it. That makes sense. I see we have a question from local audience. Yeah, please go ahead.
Yeah, hi, Andreas Biri from ETH Zurich. I have a question regarding your substrate. How far apart can these different oscillators be until it actually still works? Do you have any idea, or what kind of experiments did you do for this? Do you need them every few meters, or can they also be across the entire room?
Yes, that's a great question. So we actually did a significant amount of works in trying to characterize the scalability of larger range. So it depends on multiple factors. I would say the most important factor is how many devices you want to work at. So there is a trade-off between the number of devices you want to work versus how large you want to implement it. So if you only want to look at how much can it expand, I can tell you that we have tried and be able to synchronize them over 20-30 meters with 2 or 3 nodes. Of course, if you want to put, say, like 200 nodes, 300 nodes in there, the effective distance and area of our conductive substrate must shrink by quite much. But purely, if you want to just have a good size and a small number of nodes, we can safely be able to synchronize it across 20-30 meters, not a problem.
Okay, thank you very much.
Yep.
Yeah, Shinda, maybe you can also talk a little bit more on what you are currently working on as a follow-up of this work.
Absolutely. So going right after this project, something that is most relevant and most obvious for us to do is we want to see if we can achieve the same frequency pooling results over the air. So, I mean, what we have done over here either is coincidentally or something that's just happened to be, is that a 13.5 megahertz synchronization wave and it's the size of the conductive substrate actually makes a pretty good combination for it to be a good low frequency antennas. So in that case, we have seen over the air frequency pooling and synchronizations from across wall to wall. And that distance, I remember it was about 6 to 7 meters. So that is still quite preliminary. We would need to do more experiments and validation on that, but that would be the immediate next step and something super worth to do. Another good directions that we want to do it's in the application levels, right? So the ultimate goal for our surface bounded synchronization networks is that we want to use it for better suited for some novel applications and tangential complex environments. So if we want to implement this, say in a smart farming environment and just validate the usefulness of networks, that will also be a very valuable and valuable things for us to try.
Right, definitely, yeah. Looking forward to see the real application of this conductive substrate-based network.
Absolutely.
Yeah. Yeah, thanks, Shinda, again. And with that, I think we conclude. Oh, there's a question on Slack. Let me check. Oh, okay. Yeah, so there's a question from Raghav from UCSD. So in what scenarios is this work better than Vidyut, considering that Vidyut uses power line infrastructure, which is readily available in many places?
Yes, excellent questions. So our work differs from Vidyut in multiple ways. The most different ways between Cocoon and Vidyut is we don't use additional phase-swap loop to achieve synchronizations. So if I remember correctly, Vidyut use a phase-swap loop as the process to do frequency synchronizations. Whereas in our case, because of our requirements as well as our motivations, we directly use these physics phenomenons to frequency pool the general reference oscillators across. So that is the difference in the technical side. So the difference in the application side is that for applications or for use cases that are more general, say a synchronization requirements and needs across environments, whereas the temperature changes quite much, or some indoor-outdoor warehouse environments where power line is not available. In this case, the wallpaper or the conductive substrate that we can possibly utilize, it's probably more available than you can find a power lines somewhere in say more remote, more beloved areas or building houses rather than a nicely built indoor environments or indoor living environments. So that is the application level of difference between our work and Vidyut.
Cool. Yeah. So hope this answered the questions. And thanks all the speakers, and thank you everyone for joining this session. So this is the end of session number 2, and we will reconvene tomorrow morning for session number 3, and more precisely, I think in 14.5 hours. So thank you everyone. Yeah, hope you enjoy the rest of the day.